Am I audible? Any one of you type in the chat or speak if I'm audible or not? We will wait till 6:05 and then we will start this session. Hello, can any one of you confirm if I'm audible or not? Hello. So, hello everyone. Since it is 6:05 now, I will start. So we are in the week 5 of lecture series of solid mechanics. I am one of the TAs of this course, solid mechanics, and I will be taking the live sessions on Tuesday from 6 p.m. to 8 p.m. So now about my introduction. My name is Manoj Shikhar. I'm a PMRF scholar at IIT Delhi. I'm pursuing my PhD in applied mechanics department, and I'm one of the PMRF scholars here. I have done my BTech and MTech from IIT Kharagpur. Now in week 5, these three topics were covered in video lectures by Professor Ajit Kumar. So we will first see slight recapitulation of these lectures, and after that, I will solve a few problems. It will include both numerical and theoretical problems. Now for the notes of the course, which Professor Ajit Kumar is teaching, you can go to this link, which is shown on this slide. And from here, you can download the PDF version of the notes of whatever Professor Ajit has taught in, in the course. These PDFs, they also have some questions at their end. If you solve those problems, they will help you in for competitive exams also. I will also try to solve a few problems from there. And so without any further ado, let's start. So there are a few things we have to consider for strain. There are a few words. Stretch. It was denoted by lambda. And in actually lecture 11, professor had started this uh, discussion on strain. So there are two different kinds of strain. One is longitudinal. And the other one is shear strain. This is generally denoted by gamma. And longitudinal strains, they are denoted by epsilon II, where I can be 1, 2, 3. Now, before that, other terms which have been discussed in chapter 11 or in lecture 11 is deformation gradient. And this formula was So these are few things which we have to keep in mind before starting this chapter. Now, the basic definition which we have read about a strain was that change in length So the basic definition which you may have studied in your school was strain is change in length by original length. Or you can write it as change in length by deformed or final length. I will write it deformed length because sir has used that terminology. This condition is true if change in length was very small. Change in length was very small. I should write is very small. Then only here we can replace by deformed length. Otherwise, this is the formula. Epsilon is what? Delta L by L, where L is change in length. This is delta L. Sorry, delta L is change in length and original length is L. So this is what? Small l minus capital L by L. Then what will be L? Small l is final length of the rod or deformed length. Final length or deformed length. Deformed. Capital L is initial length. Of the body, not rod. Now, in schools, we have read that this is the formula for epsilon. But this was true for a bar, and there this was the global strain. But strains can be defined at points also, and we will see that in future. Suppose if a body is made up of many points, we can actually define strains at different points. This is x, y, z, whatever it is. We or should I say x1, x2, maybe x1, x2. So we can define a strain at a point. Few other things. Suppose this is the initial state of the body, so we call it reference. And after some deformation, body becomes like this. This is a deformed state. And suppose here if I denote the same point by small x. assume this was the point and we are denoting that by small x. So the total displacement will be, which is I'm denoting by u, will be x minus capital X. Now formula for deformation gradient can also be written as, now initially it is gradient of our current coordinates with respect to reference coordinates. That is del xi this is same as I plus gradient of this displacement vector. You can prove it by this method. You can write x equal to capital X plus u. And then if I take derivative on both sides with respect to capital X, derivative of vector with respect to itself will be I. Always remember that when you take a gradient on any quantity, its order will increase by 1. So here it was a vector, it had an order 1. Order 1. Its gradient is of order 2. So here I proved whatever I was telling earlier. So this formula will be used extensively, the formula of deformation gradient, throughout this course. Now in a general body, we generally find the strain of a line element. This is a line element of length delta x. And this is the point where this is present. So what we will do, we will first find the expression for the line element and then we will do limit delta x tends to 0. If we do limit at delta x tends to 0, what will happen? This line element will shrink to point x. And we shall be able to find what is the value at this point, value of strain at this point. We shall be able to find the value of strain at point capital X. Okay. For the derivations of the formulas of strains and all, you can refer to the lectures taken by Professor Ajit Kumar. This is just a recapitulation, so I'm not deriving everything. Whatever has been, I will just write the final expressions because that is what we will use while solving the problems today. So I'll just write the deformation gradient in matrix form because that we will need. So just for once, I will show you what will be the matrix form so that you get to see. So in matrix form, it will be del f1 by del x1. You can see that from here also. The, the row of the deformation gradient f is defined by the small x, and the column is defined by the capital X index. So if I put I equal to 1, then this means that I'm writing the first row. So when I equal to 1 and x equal to 1, I'm writing first row and first column. Now if I equal to 1 and x and j equal to 2, then I'm writing first row, second column. So instead of f, I should write xc. Sorry. This is del x1 by del x2, del x1 by del x1 by del x3. Now I'm writing second row. So the index will be del x2. Like for I equal to 2, I'm writing. So in all the columns, it will be del x2. And the term with which and for the first column, it will be del x1, capital X1, del capital X2, del capital X3. The same thing is true for the third row. Third row, I equal to 3. First column, j equal to 1. Third row, I equal to 3. Second column, j equal to 2. Third row, I equal to 3. Second column, sorry, third column, x equal to 3. So the same thing can be extended for any other gradient thing, like because in case of, suppose if I want to write like this, identity, you can directly write the identity matrix, and del x you will be written similarly. Instead of x, small x, here it will be u. The form will look similar. So it will be I plus matrix form of small u. So for x1, you will write del u1, del u2, and so. So let's have a one or two question based on this, then we will move to other topics. Suppose we are given that this is the deformation map we are given. Now, what is deformation map? So this is like how are we relating the current coordinates with the old coordinates? It is called deformation map. If I tell you find the deformation gradient tensor. So what will be the steps? So you know that you need to find the differentiation of each of the terms with respect to other current variables. So you do del x1 by del x1. What is this? 5. Del x1 by del x2. This is 4. Del x1 by del x3. It is 0. So we have found the first row of our deformation gradient tensor. Now the second row. So it will be 9x2. So this term differentiation of x3 with respect to capital X2 will be 0. Small capital X3 square differentiation with respect to capital X2 will be 0. So we will be left with 9x1. And what will it be? 2 plus 10x3, right? Differentiate this with respect to x3. So differentiation of small x3 with respect to x1 will be what? It will be x2, x3. Del small x3 by del x x1, x3. And del x3 by del x3 is x1, x2. So the first line, this is the first row of deformation gradient tensor. You can see I've written the terms here. Del x1 by del x1, del x1 by del x2, del x1 by del x3. The second row which I found is here, and this is the third row. If you like write these in the matrix form, you will get the answer. So substitute those things here, and you will find the answer. So I hope this one is clear to you, that how do you find a deformation gradient tensor if deformation map is given. So here this is the deformation map is given. Deformation map is given. Now let's see another kind of example where displacements are mentioned. Okay. Question. Now you are given u1. Suppose you are given u1 as 2x1 plus 5x3. It given u2 equal to x3 and u3 equal to 5x1 plus, maybe do it x1 plus x2 plus x3. Let us assume we have this kind of displacement with us. So this is what displacement is given. Okay. Displacement is given. Here, if I tell you find deformation gradient tensor, how will you do it? You can use this formula directly. Or the other method will be what? You find small x. So you can also write small x1 equal to x1 plus u1. You can write x2 equal to x2 plus u2. You can write small x3 equal to. Ideally, you should not do this thing because this will take more time. But I'm just showing you that this is also a method to do it. So now you have, from displacement, you have found deformation map. Suppose if I asked you to find deformation map, this is the deformation map for deformation map for above displacement given. Okay. And from here also you can find f equal to gradient of small x. So this is also one of the methods you can do. There is no harm in that. This may take slight more time possibly because you already know the differentiation of x1, x2, x3 will be I. So if I tell you find the deformation map and I have given you the displacement, this is the way to find the deformation map. Now let's move on to our original problem where we will have to find deformation gradient tensors. So first we need to find gradient of u. So gradient of u, what can we do? We first find del u1 by del x1. Sorry, by mistake, I wrote it wrong. So it will be 2. Del u1 by del x2 is 0 because there is no term which is dependent on x2 here. And del u1 by del x3 is 5. For del u2 by del x1, it will be 0. Del u2 by del x2, it is 0 because u2 is not dependent on x2 and x1. And del u2 by del x3 is 1. So this is the what should I say? This is these lines they denotes the rows of the gradient of u tensor. So to find f, what you will do, you will directly write 1 0 0. This is the identity tensor or identity matrix, and you will write the gradient of u here. So in our case, because it's numerals, I will write 2 is the first line. Del u1 by del x2 will be first row, second column. Del u1 by del x3 will be first row, third column. Del u2 by del x1 is second row, first column. Del u2 by del x2 is second row, second column. Del u2 by del x3 is second row, third column. Del u3 by del x1 is third row, first column. Sorry, here it should be u3, not u2. Del u3 by del x3 is third row, it should be del x2. Del u3 by del x2 is third row, second column. And del u3 by del x3 is third row, third column. So this is the deformation gradient matrix. If you add these, you will get the result. 3 0 1 0 1 1 5 1. Now here I have taken these deformation map or displacement randomly. So generally you should check if determinant of f is greater than 0 or not. So this is the criteria which f matrix should satisfy. So in this case, if determinant of f is 0 or not, you can check. If it is greater than 0 or not, you can check maybe by using some software or maybe by calculating it. But here I have taken randomly, like instantly in this class. So I'm not sure if it will be greater than 0 or not, but ideally it should be greater than 0. So you can check that. So we have dealt with deformation gradient tensor. Now, maybe I will check this in one day. Just give me one. Final matrix 3050191. So this matrix actually, so suppose now here I have shown you that the determinant of this matrix is -2. So this means that this displacement is not possible. Okay. So the question would have been asked like this also, that will this displacement form a deformation gradient tensor or not? So in that, what you have to do, you have to like follow all these steps, then you have to check this. So in our case, the determinant is what? Determinant of f is coming to be -2. So this displacement is not possible. So this is the condition to check. So this displacement is not possible. So now let's move on to the stretch, the relation between stretch and strain. So the formula for stretch is lambda equal to square root of one plus gradient of u plus gradient of u transpose So this is the formula for stretch. And from here, if you want to find strain at a point x with direction n, this direction n is the direction of the line element we have considered. So this is the direction, line element. We have considered. Okay. So n is the direction of the line element we have considered. X is the point at which we are trying to find the strain. So the longitudinal strain has formula lambda -1. And in this course, the assumption is that gradient of u is very small, that its order is very less than 1. So we can do binomial expansion here. And after doing binomial expansion, we can actually write this lambda -1. If we replace lambda by this thing, we can write it as 1/2 gradient of u plus gradient of u transpose this tensor is being operated on n. And this whole thing is dotted by. So this will give us longitudinal strain. Longitudinal strain along n. Now suppose if I want, if we are working in E1, E2, E3 coordinate system, let's say we are working in E1, E2, E3 coordinate system. And we want to find what is the longitudinal strain in first direction, that is epsilon 1, 1. We can directly plug n as E1. So what will happen? 1/2 gradient of u. I hope you are realizing that gradient of u is a second order tensor here. Gradient will always increase the order of the tensor by 1. So if I'm taking gradient twice, our order will increase by 2. So at n, what I will write? I will write E1. Here also I will write E1. So if you work this out, suppose if I write this by some matrix, suppose if I write by something k. So what is this? K ij into vector E1. What is the form of E1? It's 1, 0, 0. So essentially we will get k1, 1 if we solve this. Okay. So the final answer will be del u1 by del x1. That is the first row and first column element of del u plus first row and first column element of del u transpose divided by 2 will give you the epsilon 1, 1. The longitudinal strain along one direction 1, E1. For E2, similarly, we can prove that. You can also go through the lectures of Professor Ajit Kumar. There he has dealt with this in detail. I'm giving you the expressions so that I can show you some exemplar problems. So these are the formulas for epsilon 1, 1, epsilon 2, 2, epsilon 3, 3, and these are the formulas which are more general than whatever you had studied in your class 11th or 12th, whenever you have studied this chapter. So suppose if I have a bar and if I tell you what is the longitudinal strain, what you will do, if I tell you to use your class 11th concept, what you will do, you will find delta L along the, suppose if I'm telling you find epsilon 1 and this is the E1 direction. You will find the change in length. This is the delta L and you will divide it by L0. The same thing is happening here. Del U1 is what? It is the displacement. So you can replace del U1 by delta L and you will replace del X1 by L0. That is what you used to do in your class 11th. Now we will use these generic formulas. One thing to keep in mind is that while deriving this formula, we have considered that the higher order terms of gradient of u, the differentiation of we have assumed that the gradient of u is much smaller than 1. The terms of gradient of u is much smaller than 1, and therefore their squares have also been neglected. Anyways, so if I want to write like this, then what I will do, I will write epsilon 1. Okay, so epsilon 1 is what actually I am trying to find it at point X. This is the point where I want to find this train. And what is the direction? I want it along E1 direction. So this is my epsilon 1, 1. Similarly, if I want to write epsilon 2, 2, the point is X, the direction is E2. So this is the form you should write. It should be capital X1 here. Sorry. And so on. So this was about shear strain or stretch. So let's solve a problem on stretch. Maybe where is this? So this is in lecture. This is in the PDF of lecture 11 on the site of Professor Ajit Kumar, and I will be solving question number 1 here. So consider a horizontal bar which is stretched by application of an axial/horizontal force. The initial length of the bar is 1 meter, while the final length is of the bar is 1.1 meter. Which of the following statements are true? So they have given you what? They have given you they told you that there is a bar and the initial length was 1 meter. This is 1 meter. And they have stretched it and the final length is this is 1.1 meter. Okay. So what is lambda? What is lambda they are asking? So what is strain here? Suppose if this is the E1 direction. So epsilon 1 is what? Delta L by capital L, right? Delta L is what? 1.1 minus 1. Capital L is 1. So epsilon is 0.1. Lambda, and we know that epsilon 1 will be what? Stretch along direction E1 minus 1. So we can write it as lambda 1 equal to 1 plus epsilon 1. 1 plus 0.1. So stretch will be 1.1. So here is the answer. Stretch is 1.1. So answer will be B. The other method can be you can use the basic definition of stretch. The definition of stretch was what? Final by initial. Sorry. So this is how the stretch was defined, right? So the final length square by initial length square. So what is our final length? It is 1.1. So this was the definition for a square of a stretch. So what is our final length? It is 1.1 and here it is 1. This will be the value of a stretch. Now let's move on to other questions maybe. So it is telling select true or false. We have a unique value of longitudinal strain at every point in the body. True. The deformation gradient tensor can, because this is a point thing, like the strain is a point thing. So if you take different point, there will be some unique value assigned to it. It may happen that you are considering a isostrain condition, then that unique value will be same everywhere. So then that is a special case. But in general, longitudinal strain will have a particular value at a particular point. The deformation gradient tensor can be expressed in terms of displacement as, so this is the correct answer. We have already seen how to derive it. Which of the following is true? Gradient of a scalar is a second order tensor. Now, what is the order of scalar? It is 0. If I take gradient, its order will increase by 1. So it will be a first order tensor, not a second order tensor. So the first statement is wrong. Gradient of a vector is a second order tensor. The order of vector is 1. If we are taking its gradient, its order will increase by 1. So this one is correct. Gradient of a scalar is a first order tensor. This is correct. Gradient of a scalar is a vector. So vector is what? A first order tensor. So this is also correct. So in this, these three are the correct options. Now the other kind of strain is shear strain. It is the measure of change in angle between two line elements. So we have some line element x1, let's say delta x1 and delta x2. So the change in this angle between them is what shear strain is. Its measure is what we call as shear strain. So suppose if initially it was these two line elements were perpendicular. Generally we take x1 along horizontal axis. So let's follow that norm. So I'll change it. And finally, they have become like this. And this angle is what? This is beta. So initially, the angle between x1, delta x1 and delta x2 were 90. And finally, the angle between them is beta. So what is the total change in the angle between them? It is pi by 2 minus beta. Now, mathematically, how do we formulate it? So suppose if we are denoting this line element with direction small m and this with a small m. You can look at the derivation in the video lecture. I will give you the final form. So you will get something like this. Cos beta equal to gradient of u plus gradient of u transpose dotted with n. So we can replace cos beta by what? We can replace it by sine pi by 2 minus beta, or 90 degree minus beta as written by professor in the lecture. And sine pi by 2 minus beta is what? This is sine alpha. Now, one thing to keep in mind is that gradient of u is of very small order compared to 1. So this quantity itself this quantity is very small. This means sine alpha is very small. Thus, we can approximate sine alpha directly by alpha. Thus, sine alpha gets approximated as alpha. So essentially what this means is that we can write alpha equal to gradient of u plus gradient of u transpose dot n. Maybe I will replace this by equal to sign. But you should keep in mind that what are the approximations we are making. These approximations which we are making, these are being done assuming that this course is for undergraduates and this is the basic course for them. In advanced solid mechanics or in continuum mechanics, we generally do not approximate like this. But in GATE or in any other exam, generally you can directly use this formula which I have shown you. Things to keep in mind here, the shear strain that depends upon the direction of line elements which we have considered. Okay, so there are many directions can originate from the same point. Suppose if I'm taking this direction, these are two different line elements. If I'm taking this, then these are two different line elements. So the shear strain is dependent upon the line element we are taking. Dependent upon the directions of the line element which we are taking. Sorry. So we will have different values of shear strain for different pairs of lines and line elements. And one thing which was assumed at the start was that these two line elements, they were perpendicular to each other initially. So initially they were perpendicular to each other. You can see here. They were perpendicular to each other initially. That's why I was able to write alpha equal to pi by 2 minus beta. So the epsilon matrix is in matrix form is written as and we know that A plus A transpose by 2 is a symmetric matrix. So epsilon is a symmetric matrix. Symmetric matrix. Or tensor, I should say. Its matrix form will be symmetric. So epsilon is a symmetric tensor. Since this tensor is symmetric, so what will happen to the matrix form of this tensor? The matrix form will also be symmetric. That is a corollary. Now, suppose if I want to find alpha, so this is alpha mn. Okay. If I want to find alpha 1, 2, what I will do? Instead of m, I will replace it by e1 and I will replace n by e2. This will give me del u1 by del x2 plus del u2 by del x2. If you see the matrix form of epsilon, you will find that the off diagonal element, maybe I can show it from here. It should be present in this also. So if you look at the matrix form of, this is the matrix form of epsilon, the strain tensor. So you can see here it is 1 by 2 del u1 del by del x2 plus del u2 by del x1. But the shear strain which we are getting is del u1 by del x2 plus del u2 by del x1. So keep this thing in mind that when you write the matrix form epsilon, there you are actually writing half of the shear strain in the off diagonal element. Okay. So this will be gamma 1 2 or alpha 1 2, whatever notation, because we are following alpha 1 2 here. So I will write alpha 1 2. In books, you will find shear strain is written by gamma. Here it will be alpha 1 3 by 2. Now, since this is a symmetric tensor, so off diagonal element, I can directly write it as alpha 1 2 by 2, alpha 1 3 by 2, alpha 2 3 by 2, and this is epsilon 3 3. Okay. So remember these terms, they are half of the actual shear strain. Keep this in mind. Many students make mistake there. Suppose if I give you the matrix form of this epsilon, and I tell you that what will be the shear strain along the line, shear strain between line elements 1 and 2, you will have to multiply alpha 1 2 because you will have to multiply epsilon 1 2 by 2. So maybe this is epsilon 1 2. Okay, so you have to write alpha 1 2 by 2 equal to epsilon 1 2, and then you will write alpha 1 2 as 2 epsilon 1. Okay, so let's do an example here. Maybe by example, you may be able to remember this. Suppose I give you epsilon matrix as so since this is symmetric, what should this be? It should be 0.03. What should this be? It should be 0.02, and this should be 0.01. Okay. If I tell you write the find the components of strain, then longitudinal strains, what will be those? Epsilon 1 1 will be what? 0.1. Epsilon 2 2 will be 0.15. Epsilon 3 3 will be 0.25. This thing. Now, if I write shear strains, so alpha 2 1 2 will be what? 2 times epsilon 1 2. So it will be 2 times. Maybe I should write it as point maybe 0.04%, because I don't want people to confuse here. I took last one as. So the answer is what? 2 into 0.01. So 0.02. Alpha 13 will be what? 2 times epsilon 13. So 2 into 0.04. That is 0.08. Alpha 2, 3 will be 2 times epsilon 2, 3. That is 2 times 0.03. So this is how you extract strains from a matrix form of a strain tensor. Now, this was a very basic question, and I don't think you will get it directly in exam, but this question will actually clears your concept that many people make mistake. They will directly write alpha 1 2 as 0.01 and that they will get the answer wrong. Now, volumetric strain. These are denoted by epsilon V, and the formula is trace of epsilon matrix. So this is epsilon XX plus epsilon YY plus epsilon ZZ, or epsilon 11 plus epsilon 22 plus epsilon 33. So volumetric strain does not depend upon the line element we are taking, because if you remember from our past discussion, the trace of any matrix is one of the invariants. It does not change with change in the form of matrix representation. So epsilon V will not depend upon the line elements you are taking. In other form, you can directly write it as change in volume by original volume. Delta V by capital V. Now, if we can also write this as trace of 1 by half of delta U plus delta U transpose. So essentially, three things to keep in mind. Longitudinal strain, along direction n, that is the direction of the line element is n, is 1 by 2 gamma mn, or what I was writing earlier was alpha mn, is 2 times And epsilon V, the volumetric strain is what? Trace of 1/2. So I hope you can see that half of gradient of U plus gradient of U transpose is a very important term. If you find that, you will be able to find the components of strong along any direction, like the longitudinal strain along any direction n, or the shear strain between two line elements, or the total volumetric strain. You can also read about the physical significance of these in the video lecture. Sir has explained that what is the physical significance. Now another concept which was introduced was the rotation tensor. So sorry, the rotation string, the rigid rotation of a body. So local rigid rotation, I should write, because by rigid rotation, you might consider that the whole body is getting rotated by the same amount. Till now, if anyone has any doubt, they can ask, because after that I will go on to solve a few problems. So if you have any doubt in any questions, you can ask. And I request you to not to ask any questions which are currently the part of any active assignments you are having. I won't be able to help you with those. We are instructed not to help you with those as well. So the deformation gradient tensor can be written as this, right? Now, if you remember, we can decompose any matrix into a symmetric part as well as a skew symmetric part. This is class 12th matrix algebra. If you were in CBSE, of course, I was from CBSE, so we were taught in class 12. So what did we do? We added gradient of U transpose by 2. And now we will subtract gradient of U transpose by 2. Okay. So this part is symmetric. Symmetric. This is skew symmetric. So F is written as I plus, what is this? This is the strain tensor, epsilon. And what is this? We denote this by W. Okay. W is a skew symmetric matrix, so its diagonal term will be 0. And we can also think W as that it will denote the angle of rotation as well as the axis about which we are rotating the body. Okay, so you can find this concept in lecture 13. Sir has discussed it around 46, like after 45 minutes of the lecture, you will find this concept there. I just wanted to write it here so that you get, like, your concepts get revised. So this is the axial vector of W, this tensor W, and this is denoted by 1/2. if you remember the first lecture where tensor calculus was discussed, there this concept was shown that how do you create a skew symmetric tensor from a skew symmetric second order tensor from a vector, and vice versa. How do you create an XL vector from a skew symmetric tensor? So you can also refer that lecture, that how to make this skew symmetric tensor of this W. Sorry, how to find the XL vector of this W. So sorry. Okay. Now there are a few concepts I would like to say those are similar to what we have read in stress. So principal strain. Suppose if you are given epsilon matrix and if they tell you in matrix form they are given, they tell you that find the maximum, find maximum and minimum strains for this. This means that they're telling you to find the principal strains. So what you will do, you will find the eigenvalue. Find the eigenvalue. Answer is find eigenvalue of epsilon. Okay. Find the eigen. I'm writing E as epsilon, sorry. Find the eigenvalues of epsilon. If they tell you to find the maximum shear stress, maximum shear strain, maximum shear strain. We will follow the similar method we did for the maximum shear stress. Okay. And why are we able to do this? Like, we are able to do this because both stress and strain matrices which we have, they are symmetric. So their properties will be similar. I'm like not discussing these in details because I have to like solve one problem with which is related to compatibility equation and it will take some time. So I'm rushing this. Huh. The same in the same way you can like find the deviatoric part or the hydrostatic part of the strain tensor. So you can do that in the same way. You can find the invariants. You can find the invariants here. You write J1, J2, J3 and invariants. Invariants of a strain tensor. So essentially these tensors in their matrix form, they're just some matrices, like some symmetric matrices. So that's why the properties are similar. They are not same, but they are similar because in stress, you generally talk about plane, you talk about point. In strain, you talk about line element, not plane. So where is this? Yeah. So the topic which I want to discuss and I will solve a big problem related to this is strain compatibility conditions. So the one thing to keep in mind here, we assume the form of epsilon is the form of epsilon is. And then we think that, okay, can any epsilon is, can any form of the epsilon is will give me a plausible solution for displacement? Because at the end, we are having the physical thing which we are having, which we can see is the displacement of the body, like the displacement of the points of the body. Now, any tensor can be a symmetric tensor. Even this tensor is a symmetric tensor. Why? The property of a symmetric tensor is Aij should be equal to Abi. If I write it as 10 to the power 5, this is also a symmetric tensor. Even if I do suppose I do 156, this is also a symmetric tensor. But if we have a strain tensor with this much strain, either the material is very elastic, it can be elongated very long, or the material has broken. So not any form of a strain tensor is acceptable, or they will give the right displacement solutions. So to keep this thing in check, strain compatibility conditions have been defined. Okay, so I will just give you the strain compatibility equation directly so that we can move on to the problem I want to solve. So what are the strain compatibility conditions? So there are 6 strain compatibility equations. The first one is so to remember these, you can distribute them among 2 different kinds. Like remember it like this. So you see here we have strain along x-axis. It is getting differentiated with respect to y twice. Strong along yy is getting differentiated with respect to x twice. And here we have shear strain, I mean longitudinal strain, Here we have shear strain which is in between the elements x and y. So the other 2 equations related to these will be, suppose if I'm writing epsilon xx, maybe I will just export this to save this so that I do not lose this. So suppose if I want to write gamma xz on the right, so what I will do? I will take epsilon xx, I will differentiate with respect to del z square. Sorry, I will differentiate twice with respect to z, and here it will be epsilon zz. It will be differentiated twice with respect to x, and on right hand side I will write gamma xz by similarly, if I want to write for yz, I'll write del epsilon yy differentiated twice with respect to z plus del epsilon zz differentiated twice with respect to y. So these three can be grouped together, and the other forms are, so you're differentiating with respect to some variable z. So here the series train which contain z, they will come with positive sign. Okay. Now here you can see the series train is yz, so it is getting differentiated with respect to x. So if I write gamma xz, it will be getting differentiated with respect to y. And the third sphere which does not have z, which is yx or xy, whatever you write, it is a symmetric thing. It will be getting differentiated with respect to z. And on right hand side, you will have the longitudinal strain along the same variable which about which you are differentiating here. Okay. Suppose if I want to differentiate with respect to y here, the C restraints which will come with positive sign will be gamma yz getting differentiated with respect to x plus gamma yx minus gamma zx, which is getting differentiated with respect to y. It should be capital Y actually. It should be capital Y. And which strain will be here? It will be epsilon y. And in the bottom it will be del x del z. Okay. And the last but not the least, I hope while writing this you are trying to remember in mind what should be the sign here, what should be the term here, what should be the differentiation with respect to which we are taking. Okay, then it will be easier for you to remember. So I will take a few minutes of break here and then we will again continue. And this problem will be probably the last question of today's class, which I will deal right now. So, and if time permits, maybe I will discuss the other questions from PDF I have downloaded from such website. So few of you can write codes in different languages for fun. Maybe you can try to write codes for solid mechanics problem. You can use Python, that is a free software. If you have access to MATLAB, you can write on MATLAB. It's quite easy. You have to just follow some notes or some help pages from on Google, and it will help you a lot. For me, coding actually helped me to visualize different things. Like it helped me to check whether my answers are correct or not more easily than, for example, I checked if the determinant of f was coming to be positive or not, and I realized it is -2. So I knew that if the determinant is not greater than 0, then this is not a possible displacement wave. So those kind of things, insights, coding helps you to get them very easily and repetitively. If any one of you have any doubt, you can ask me. Otherwise, I will move on to solving the new problem, the last problem probably. Now, one special case of this compatibility equation is if you are given a plane strain condition. Plane strain condition is what? The strain in a direction. So suppose if we have a plane and we are taking in plane axis as x and y. Okay. Suppose this is y and this is the outer axis z. So epsilon xx, epsilon yy, and epsilon zz will not be, oh sorry, epsilon xy will not be 0. Not 0. But the out of the plane, like whatever has z, like maybe I should write gamma x z xy here because we are talking about shear strain. Gamma xz, gamma zy, and epsilon zz, these are 0. Suppose if the plane was yz, then epsilon xx, gamma xy, and gamma xz were 0. So these are called the condition of plane strain. And there, our we like 5 of the compatibility equation gets automatically satisfied. So there we need to check only one compatibility equation. For example, in this case, If you put epsilon zz 0 here, gamma xz, gamma yz 0 here. Okay. So what you will get? You will get differentiation of z with respect, sorry, differentiation of gamma xy getting differentiated twice with respect to z. Now we know that gamma xy does not depend upon z. You can see that there is nothing outside the plane, like gamma xy will not depend upon z. So this will get automatically satisfied. Anyways, so the only compatibility equation we have to check will be the first one. So I will write it down here. So let's use the trick. If I am taking epsilon xx, it should be differentiated with respect to y square. If I am taking epsilon yy, it should be differentiated with respect to x square. I will have to take the same gamma xy and I will differentiate with respect to x and y. So this is the compatibility equation we will have to use. Now the question is, given the following formula for strain. Following formula for strain components. And the formula they have given is epsilon xx equal to 5 plus x square plus y square plus x to the power 4 plus y to the power 4. Epsilon yy is 6 plus 3x square plus 3y square plus x to the power 4 plus y to the power 4. Gamma xy equal to 10 plus 4xy into x square plus y square plus. Okay. So they have given you the form of strain components and other components are 0. They've given epsilon zz equal to 0, gamma yz equal to 0, and gamma xz equal to 0. This means what? This is the condition of plane strain. After reading this, you should realize plane strain condition. Plane strain condition. So 5 of the compatibility equation have already been satisfied. I have to just use this one. So the questions, the follow-up questions are, first one is determine whether the above strain field is possible. The above strain field is possible. Why they have asked this question? I've already discussed. Any symmetric tensor cannot be a plausible strain tensor. There could be some abrupt values in those strain tensor, in those symmetric tensors, which do not make sense in physical world, or they don't have any physical significance. Like I showed you, if I give you a strain of 10 to the power 5, that doesn't make sense. So we have to check whether the strain field we have considered, like these are the assumed strain field, like these are something which we are considering ourselves. So we need to check that whether these will follow the norms or not. Okay. Now, if these are possible, if these are possible, the question is determine the determine the displacement components. Displacement components in terms of x and y. Terms of x and y. And they have given you some things like assume that ux equal to 0, uy equal to 0, and wxy equal to 0 at the origin. So they've given you a boundary condition that the displacement of origin along x direction, the displacement of origin along y direction, and the rotation of the line elements x and y is 0 at the origin. And the second part is find volumetric strain. Volumetric strain. Hydrostatic and avionic strain tensors. Strain. So this is the complete question. Now you have given epsilon xx. You have to use del 2 epsilon xx by del x del y square. So these term will, if you differentiate epsilon xx with respect to y twice, this will be 0, this will be 0, this will be 0. Only the contribution will come from y square and y to the power 4. So I will directly write del 2 epsilon xx by del y square will be what? It will be 2 plus 12 times y square. Maybe I should show you the steps also. This is what 2y plus 4y cube. Now, if you differentiate it with respect to del y square, should be capital Y here. I'm so sorry. Maybe I should change the color of the ink also. Ink. So this will be what? 2 plus 12 y square. Now, what will be del 2 epsilon y by del x square? So any term dependent on y or only y or constant will vanish because we are differentiating with respect to x. The only contribution will come from 3x square and x to the power 4. So from 3x square, we will get 12, sorry, 6, not 12. Plus 12x square. Okay. And for gamma xy, we have to differentiate with respect to x and y. Okay, so the first term will be 0, but this term will have a good contribution. So I will write it here. Maybe for this, I will have to show you the complete step. 10 plus 4xy x square plus y square plus 2. So it's better to write it. Now del gamma xy by del gamma xy by del y is what? So the first term will vanish. This is so it will be 8x plus so if I differentiate del gamma xy, so if I differentiate gamma xy with respect to y, what will I get? I will get 4x cube plus 8y square x. Now I have to differentiate the above expression with respect to x. Okay. So what I will get? I will get 8 plus 12x square plus 8y square. Oh, sorry, it should be 12. It's hanging a lot. Why does it happen every day? So it should be 12y square x. So here it should be. Now we substitute these in this compatibility equation and see if LHS equal to RHS. So let's substitute LHS. So you can see the first term is 2 plus 12y square. So it will be 2 plus 12y square. From the second term, it is 6 plus 12x square. So it is 6 plus 12x square. So what is this? 8 plus 12x square plus 12y square, which is equal to, if you see from this equation, this is equal to del 2 gamma xy by del x del y. Okay. Thus, we can conclude that the above strain field is possible. Since LHS equal to RHS, we conclude above strain field is possible. Strain field is. Now, since it is possible, we will have to solve the second part, which is determine the displacement components in terms of x and y. Assume that ux equal to 0, uy equal to 0, and wxy equal to 0. Okay. So this is where the trick will happen. Anybody has any doubt? Okay. So what is epsilon xx? This is del ux by del x, right? This is epsilon xx. So what we can do? We can write ux as integration of epsilon xx dx. So ux will be what? Integration of 5 plus x square plus y square plus x to the power 4 plus y to the power 4 dx. So this is what? 5x plus x cubed by 3 plus y square x plus x to the power 5 by 5 plus y to the power 4x plus some function of y. Why, if you have already studied partial differential equations, you may know like why did I write f of y? But I want to say that for other people that you see what is epsilon xx. This is differentiation of ux with respect to x. So what happens if I differentiate a function of y with respect to x? I will get 0. So ux may have a term which is just the function of y, and when it was differentiated, we only got these terms. So that's why, that's from where, so that is the place from where the significance of this fy is coming, that ux may have some f of y, which was which became 0 when I differentiated with respect to x. So I need to consider f of y while integrating. Also, this is an indefinite integral. So I need to consider the constant term here. So the constant term with respect to x will be what? Anything which is not dependent on x. So f of y can be treated as a constant term because we are integrating with respect to x. Similarly, epsilon yy is what? It is del uy divided by, sorry, differentiated with respect to y. So we can write uy as, okay. So let's replace uy, sorry, epsilon yy here. So what will be ui? By same logic, we will have some function of x here. So first I will write 6y plus 3x square y plus 3y square, sorry, y cubed by 3. So I will get x cubed directly. Sorry, y cubed directly here. Plus some function of x. Now it's not necessary that the function of y and function of g x will be same. Okay, they can be different functions. I hope you people are understanding what I want to say here. Now gamma xy is what? Gamma xy is del uy by del x plus del ux by del y. So we have expression of ui here, we have expression of ux here. Substitute that here and you will get 2xy. Should write. We will get 2xy plus 4xy cube plus f prime y plus 6xy plus 4x cube y plus g prime x. Okay. So let's arrange the terms. 2 plus 6, 8xy plus 4xy cube 4x cube y plus f prime y plus g prime x. Also, if you see, you have been given the expression for gamma xy here. This is 10 plus 4xy x square plus y square plus 2. So we can equate this equation. So we can replace gamma xy by 10 plus 4xy into x square plus y square plus 2. X square plus y square plus 2 equal to 8xy plus 4xy cube plus 4x cube y plus f prime y plus g prime x. Okay. Now g prime. Okay, one thing to keep in mind: f prime y is differentiation of f with respect to y. G prime x is differentiation of g with respect to x. Okay. So if you see, these terms will cancel. And you will get what? You will get f prime y plus g prime x equal to 10. So this is one of the equations. So from here, you can write f prime y equal to 10 minus g prime x. Now on left hand side, you have y and on right hand side, you have x. This means that g prime x is a constant. G prime x is a constant. Also, f prime y is also a constant. Why? Because left hand side is an explicit function of y, right hand side is an explicit function of x, and x and y are independent variables. So LHS and RHS must be constant for this expression to be satisfied. This means what? F prime y is a constant. G prime x is a constant. So suppose if I write gx is, so if g prime x is a constant, that what does that mean? Its integration will be a linear function. So g prime x is this, so gx will be what? And let us say this constant is d, which I am telling, because f prime y is d. Let us assume we write it as d. So what will be this? G prime x will be 10 minus d x plus some constant. Let's say this constant is c3. And fy will be what? Fy will be dy plus some constant t2. Now you have been given the initial boundary conditions that ux at x equal to 0 is 0. So what will you do? You will do ux equal to 0 from here. Ux at x equal to 0 and y equal to 0, like the origin, right? Y equal to 0 is 0. So you have to put ux 0 comma 0. So if you look at the expression of ux, you will get f of 0. So f of 0 is what? C2. This is 0. So from here, we get C2 equal to 0. Uy x at x equal to 0 and y equal to 0, that is the origin is 0, implies that uy 0 comma 0. So what you get it as z0. If you look at this, the condition for uy, the expression of uy, if you put y equal to 0 and x equal to 0 here, you will get g0. And they have given it as 0. So in this expression, if I put x equal to 0 and y equal to 0, I will get c3. So c3 equal to 0. So from here, I get c3 is 0. We also have another expression wxy at origin is 0. Wxy. Its expression from you can get from the last lecture of sir. So the expression of wxy is 1 by 2 del ux del y minus del uy del x. Hanging a lot. And we have to put x equal to 0 and y equal to 0 in this expression. And we have to equate it by 0. So if you work this out, del ux by del y at x equal to 0 will be what? F prime y minus z prime x. And you have to put x equal to 0 and y equal to 0, and you have to equate to 0. This means that f prime 0 is equal to g prime 0. Now for any linear function, that its differentiation is what? The slope of the function. So if you remember y equal to mx plus c. So this is suppose z equal to my plus c. So what will be the differentiation of f with respect to y? It will be d. And if you put y equal to 0, still you will get the same value. So from here you are getting f prime y equal to d. From here you are getting g prime x equal to 10 minus d, which we already had here. So f prime 0 will be what? D. This will be equal to 10 minus d. This means d equal to 10 by 2. This means 5. So now we have the expression of fy and fg. So fy is 5 times y and gx is 5 times x. So if you substitute in ux, substitute this in uy, and you will get the displacements. Okay. Now for part B, I will just give you the steps you have to follow. The step is now you have ux and uy. You can find the gradient of u. Step 1, find gradient of u. Step 2, find strain tensor, find epsilon. How will you find it? 1 by 2 gradient of u plus gradient of u transpose. After that, trace of epsilon will be volumetric strain. And you can use the formulas sir has given in class to find use formula sir derived in class. Sir has given in class. Given in class to decompose epsilon tensor into hydrostatic and dilatoric parts. Okay. So I hope this question has made many of your concepts clear. So if anyone has any doubt, they can write in the chat or after. Otherwise, I will end the session. We are already running out of time. So if anyone has any doubt, kindly write in the chat. Jatin, Rahul, Adarsh, Kiran, Gaurav, Sarthak, Raunak. Anybody has any doubt, then you can write in the chat. You can also unmute yourself and tell. Since none of you have any doubts, I will end this session now. Thank you for joining this session. I will again take session for week 6 in next class on Tuesday from 6 p.m. to 8 p.m. You can join my lecture there. I'm also uploading these videos on YouTube channel as suggested by NPTEL team. So you can go and check these videos again. If you have any other doubt, you can write doubts in the dashboard or discussion forum on the SWAYAM. So thank you everybody for joining. Have a great day. Bye. Yeah, hello. Yeah, Kiran, do you have some doubt?
No, sir.
Yeah.
What
doubt do you have?
No. I am not.
Oh, you don't have any doubt. Okay. Yes.
Okay, thank you. Bye.
Thank you, Kiran. Bye. Thank you.